Welcome back to the OpenGL 3D game engine series. In this episode, we'll draw our first square, but first we need to set up a window. Let's clean our program.cs file by deleting everything that's in it. Now we'll right click and create a new folder, the engine folder, which will contain all engine files. Here we'll add a new item, the window manager. So the window manager will have three properties. First, a public static window. For this, we need to include GLFW, a public static vec2 for the window size, and at last, a public static vector4 for a clear color. Now we're going to write a new method, static unsafe void create window. Here we'll set up our window using GLFW. We'll take in a width, height, and a string title. So we'll set the window size to be width and height. And we'll start GLFW. Now we'll run glfw.init. This will allow us to run all other glfw methods. It also returns a bool if glfw is correctly initialized. Now we could handle that error, something we could do later, we won't right now. We'll set up these three window hints. This will define the OpenGL version 3.3 core. The context here is referring to a specific OpenGL context, which is a specific instance of OpenGL for our window. And we're setting its version to 3.3 core. Next, we'll also set some other window hints. We'll set the window to be focused on startup and to not be resizable. I will create our window. Create window method requires us to define the width, height, and title of the window. We are using none, so therefore we'll just create it on the main monitor. And at last, we could define a parent window. So if you were to start a pop-up window, you could share the OpenGL context over these two windows. Now we'll check if the window was created correctly. So if the window were to be window.none, window creation would have failed. So we just write to the console and return. You could in theory also throw an error here or do something else, but that's up to you. Here we are fetching the size or the rectangle of the primary monitor. This we are doing to find out where the center of the monitor would be and placing our window there. We really don't need to do that, but it's just nice to have the window centered on startup. So now we're going to include all OpenGL functions, as we talked about in the last episode. For this, we need to create the using to use the OpenGL.gl file, but it is important to define it as static. This means that the GL file behaves as if it were in this class. So we can just call this method instead of needing to place a GL dot in front of it. We are also now going to create a OpenGL viewport with the specified sizes of our window. Now an OpenGL viewport could also be off-center or smaller than needed, depends on what you want. But we want it to cover the entire screen, so we'll make it full-sized. Notice how we don't need to define gl.gl viewport, because again, we are including the OpenGL.gl file statically, therefore we don't need to write it at all. Now we're going to set up some OpenGL and GLFW settings. The first one is quite important. That is stop interval, or in other words, vsync. We're going to turn that off. These are some other settings we're going to set. First is the clear depth. This is just what value the depth buffer will be set to when it's cleared. Here it will be set to 1. Next, we're going to enable GL blend and set the GL blend function to this. GL blend is just how OpenGL will blend two transparent surfaces because the colors need to be blended somehow. And there are several ways to do it. We are just going to use this function here. Another thing we're going to do is enable the depth test, because again, our game is going to be 3D and using depth. And the GL depth function will be GL less than or equal. These are very standard settings, which most GL games will have. So here, we're going to handle GLFW errors. Can do that with the set error callback. Now a callback here is just a delegate, the error callback delegate. If you don't remember what the delegate is, or if you don't know what the delegate is, there are many videos explaining it. It's something that points to a specific function, which GLFW can later run. And the function here is of type error callback. Now the error callback delegate takes in two parameters. One is the error code and two is the error message. And we're just going to write the error into the console like that. So now that we have our window created, we just need another function to close the window. So here we're calling destroy window to destroy, or in other words, close the window. And then we terminate glfw, which should finally clean everything up for us. So we should be done, and we now should be able to create our window in the program.cs file. So we're going to write window manager to create window, specifying our size and the title of our window. Now at the end of our program, the window should close. In the middle here, we're going to write a while loop. We're going to loop as long as the window doesn't need to close. And here we need to tell glfw to poll the operating system events. Here all events, stuff like the window should resize, the window should close, and inputs and other stuff coming from the OS will be handled. At the end here, we're going to call glfw.swap buffers. So what this does is every active window on the computer has two buffers. A buffer is just a list of data. Here we're talking about a list of pixels. One buffer is displayed to the user and the other buffer is constantly updated. glfw.swap buffers will swap the render buffer and the display buffer, presenting the thing that we were rendering. Or in other words, this defines the end of a frame. So in here, we would render, and before rendering, we would update. Now, if you press play, our window should appear. And whoops, we get an error. I forgot to add the current glfw context to this specific thread. This does nothing else but specify that the window we are using right now is owned by this specific thread. Now, if we try again, it should work and we see our window. But sadly, it's just completely black. So let's close it, go back to program, and here we can clear our buffer. You need to include OpenGL to GL, and we're going to set the GL clear color to the color we have defined in the window manager, like this. So the window will be cleared with the color defined in our window manager. And now we're going to run the GL clear command on two buffers. Again, our window has many buffers, but the two we will need the most is the GL color buffer bit and the GL depth buffer bit. So now up here, we will change the window manager's clear color to some other new color. This should give us purple. Now we get two errors. One is that vector4 is not defined. Here we just need to use system.numeric. And the second thing is that I accidentally defined clear buffer as a private set. It should just be public. Now we overwrite the clear color. And if you run the program, should get a purple window. Now we have the first step done and we can go to rendering our square. When it comes to rendering using OpenGL, we need to understand some basics first. One of the things that makes OpenGL somewhat difficult to understand is the way one needs to work with objects. OpenGL is not object-oriented, but it does use objects in some ways. Here, for example, we are working with an object. In OpenGL, objects are defined with a specific index. Here we have an index or an int VBO. The VBO is set to a value of glgen buffer. If we want to edit this buffer, we need to bind the buffer with the ID, and then we execute some functions, and these functions will edit the binded buffer. If we're done with editing, we will unbind the buffer, which just means to bind 0. This is very much different to the way we do it now, which is using objects and editing the object's data. But if you understand this concept, it makes working with OpenGL a lot easier and a lot more intuitive. Another thing is you need to understand the OpenGL rasterization pipeline. This image shows it really well. Here we will pass the input geometry to the GPU memory. Then when we call the render function using OpenGL, it will go through this process. All blue squares here are unchanging, so we do not have a chance of editing. All green squares are things we will program or change later. Primarily we will change the vertex shader and the fragment shader. As you can see here, it makes very clear what every shader does. In the vertex shader, we define and move specific points here. These points are the vertices. In the rasterization step, a pixel will be drawn between the vertices. And in the fragment shader, we will change the color of these vertices. The fragment shader edits a specific fragment, or in other words, pixel. And the vertex shader edits a specific vertex. At the end, we'll get our output buffer, the so-called frame buffer, which we are swapping onto the screen using GLFW. Now, the question is, how will we define that data? OpenGL gives us a very simple tool for this, the so-called VBO. A VBO is nothing more than a list of vertices. And a vertex is nothing more than a series of attributes like position or color or something else. Here you can see how it would be laid out. You have every vertex in green and every attribute in red here, and they would be set up in series. An attribute has a specific index, which then allows us to read them out in the shaders. A VAO is just a list of VBOs. For now, we're only going to use one VAO and VBO, but later we may add some more VBOs. Let's start to put this together. We're going to create a new class, and we're going to call this model. Now model will take in our vertex data and create a VAO and VBO from it. So we need a private uint VAO, which will contain the ID of our VAO, and a private uint VBO, which will contain the ID of our VBO. We also want to store the vertex buffer size for later. So now we can create the constructor. The constructor will take in a list of floats, which is our vertex data. The vertex buffer size will just be the number of elements in the vertex data array. Now we're going to create our VAO. Again, we need to include OpenGL statically. And we're also going to create our VBO, which will just be a normal buffer. Now we'll bind our VAO. Again, we need to do this to tell OpenGL that we are working with it and that all other commands will edit this specific VAO. And we will bind our VBO. We also need to specify what type of buffer it is. It's a GL array buffer object. It seems like I forgot to say this before. Again, VAO and VBO stands for vertex array object and vertex buffer object. So in a sense, we are doing object-oriented programming. Instead of passing objects, we're just passing the ID. Now we need to pass the data to OpenGL. This is going to be a little complicated. We're going to define a fixed area. In a fixed area, we have complete control over memory. And what we are doing here is we're reading out the memory address of element 0 of this list. So float.pointer now points to the specific memory address where our buffer is stored. Again, in the C world, this is the way you work. So you point it to a specific memory location where data was, and another function would read out of there. Nowadays, we wouldn't do it like that. What we're going to use here is GL buffer data. This will set the data of the binded buffer to what we pass it. It takes in 4 arguments. The first one is the target. We set the target GL array buffer, which is bound to our VBO. Then we're going to specify the size in bytes. First, we're going to get the size of a float, which should be 4. And we're going to multiply that by the length of our array. And then we're going to pass the pointer to our data. At last, we're going to define our usage. For now, it's going to be GL static draw. So we're not going to update the data, and we're going to use it to draw. This will tell OpenGL how it will store it in memory. You could also define it as dynamic draw, which would mean that OpenGL has it in a location where it could edit it faster. Or in other words, the graphic card would store the data in a location where it could be updated faster. Now we're not going to update our data here, so we're not going to define that. Now we need to define our vertex attributes. Remember, a VBO is nothing else but a list of vertices, and a list of vertices is nothing else than a list of attributes. Attributes can be any type of data. We're going to have 2 attributes, attribute 0 and attribute 1. The first attribute here is going to be position, and the second one is going to be color. Here we are defining the settings of this attribute. The first argument will define the index, which will be 0. The second one, the size. We have 3 floats, so the size will be 3. Then we're going to define the type, which will be GL float. Fourth argument defines if the value should be normalized, which we won't, should be false. And the next argument here defines the stride. Now, what is a stride? A stride is how much does OpenGL need to jump to find the next element. A list of two attributes. We have X, Y, Z, and then RGB for the first vertex. Then we have again X, Y, Z, RGB, like that. For every vertex, we have those 6 attributes. If OpenGL wants to find the next attribute, so the next position attribute, the stride will define how far it must jump for it. So it must jump 6 floats. And if you look from X here, it only takes 6 jumps to get to the next X. So what it will do is it will read out 3 elements, then jump 6, then read out 3 elements, then jump 6, and then again read out 3 elements for the position attribute. The same will be done for the color attribute, but the pointer, and the pointer defines at what position it will start, is offset by 3. So we won't start here, it will start here. So from 3, it will read out 3 elements, then it will jump 6, read out 3, jump 6, and read out 3. This is kind of difficult to grasp, but this is how you would define data in the C world. So now we have defined our vertex attributes, position and color. Lastly, we need to unbind our buffer and we're done. Now our data lives on the GPU. Just need 2 other methods. First thing is a way to bind the VIO and a method to unbind the VIO. This will be needed later to render our object. Then we need a way to read out the size of our buffer. At last, we need a way to destroy our model or our data. So first we're going to delete the VBO, then the VIO, and we're going to set them to 0. Now the problem is you're probably going to forget to execute this delete method. So we'll just create a little destructor. So the destructor is ran when the object is at the end of its life cycle. And here we're just going to call delete, which will destroy our model. So all of this will represent a model in our game engine. Let's go back to our program and let's define some data. The vertices will look like this. And from this data, we will create a model. I'll have this in the description, so you don't need to write this yourself. Here you can see we define 6 vertices, and both of them make up 2 triangles, one at the top and one at the bottom. You will notice that it builds a square, a 1 by 1 square. Now, if you wanted to render this object, really the only thing we need to do is bind it and to run the GL draw array method. Now it takes in 3 arguments. The first one is what type of element we want to draw GL triangles. Then it will ask us what element we want to start with. We want to render the entire array. So we'll start with 0 and then the size or the count of the array. We have that stored somewhere in the model.vertex buffer size. At the end, we will unbind our VIO and we're done. So now if you were to run this, you may or may not get a square. Now this may depend on what your graphics driver actually does. It may also just be completely pink for you. To actually get this to work properly, we need to define the shaders. So we create another class, shader. Now the shader class is going to be a little more complicated. Our shader will both contain the vertex and fragment shader. And we will store the file path here at the top so we can identify what shader is what. Then we need to store the program ID. Like with the buffers, we will be working with IDs instead of objects. Now we create the shader constructor. So we read in the vertex and fragment file path and store it. And then we're going to try to load the data from it. We will read out the file text. We're going to use file.readload text here. And we're going to do it in a try catch block because it could fail. We're going to put out an error if it fails. And we're going to store the source code in these 2 variables. We're going to create a new method called createShader that takes in the vertex and fragment code. And we're going to call it from the constructor, passing in the vertex and fragment code. In here, we're going to create a new program using GL create program. We need to include GL statically. Then we need to write another method which will return a uint, and we call that compile shader. This method will compile the specific shader, and it takes in a string code and an int type. Now in here, we're going to generate a new shader, specifying its type. We're going to specify the source using GL shader source, passing the ID, and then we're going to call GL compile shader, again passing the ID of the specific shader. And now our shader would be compiled and we could return the ID. But it's smart to do error checking here because shader errors are sometimes quite difficult to catch. So we get a shader IF, which is just information about the shader, passing the ID. And what we're going to read out is GL compile status, which tells us if the shader was compiled or not. and going to pass that to the result. I forgot to specify that this method is unsafe. If the result is not equal to GL true, so if the file did not compile correctly, we're going to read out the shader log or shader info log, which will tell us what error happened. And we're going to write that to the console. Like up here, we're going to close the program when a shader fails. Now we are successfully checking for errors. And if errors happened, we would close the program. We also are, so now we can compile a shader successfully. Up here in the create shader method, we will first compile the vertex shader to see the vertex code. And with the type GL vertex, then we're going to do the same with the fragment shader source code, and define the type to be fragment shader. Now we have these two shaders, and we're going to combine them into a program. A program is the word for the final pipeline that GL is going to use to render out. So we will attach a shader to our program, first the vertex shader, then the fragment shader. Then we're going to run GL link program. This will link our two programs together, because the vertex shader can pass arguments to the fragment shader. And then we're going to delete our shaders. Now, after linking, the shaders are now part of the program, and therefore we can unlink those separate shaders and delete them. So now we are cleanly loading shaders, checking for errors and linking them together to a program, which you can then use for rendering. There are another few things we need to add to the shader. First, we need to add a method to bind and unbind the shader, very similar to the model class. And then we need a delete method, again, very similar to the model class. And up here, we are going to create a destructor, which we call the delete method. And in the delete method, we're just going to delete our program. If we go back to our program, up here, we can now create a shader. So now we need to actually write the shaders themselves. This is made easy because we have the bin dep folder. In here, we can just add a new folder, call it shader. And in the shader folder, we create two files. We'll call it model shader.bs and another file, model shader.fs. Both of these we will load in up here. So the path will be, because bin dep will be copied into our binary folder, the path will be just shader / model shader.bs and the same for the fragment shader fs. Now we need to actually write those two shaders. A shader code is quite simple. It's very close to C code, so I don't think you will have that big of a problem understanding it. The first thing we need to define is the actual version we're using. This is done by writing hashtag version 330, which stands for 3.3 core. Again, this is what we specified with GLFW. Now we're going to read out our attributes. So this may be a little complicated to read, but it's quite simple. The first part here tells us how our attribute is laid out. It says that the location of it is 0. The second part tells us what is actually coming in, and it's a vector 3. A vector 3 just represents 3 floats. We're going to call it a position for attribute position. We're going to do the same thing for the color. We're going to write a main function here, and we're going to set the GL. Now, what does this line mean? GL_position is a pre-made variable by OpenGL, and it defines this on-screen position of the vertex. Now, the OpenGL coordinate system is somewhat weird. It is a 2x2x1 square, where the center is coordinate 0, 0, and it ranges from -1 to 1. So you have -1, 1, -1, 1. Depth is just 1. Here, we are defining this GL position to be our position. But the GL position is not a 3-dimensional, but 4-dimensional. You have also a W value. Why, you will see later. But for now, we're just going to set this to 1. You can see here another feature of OpenGL shaders, or more specifically GLSL, which is you can pass a vector 3 in a vector 4 and just define the missing attribute. You can also read out attributes just by writing .x, y. So now we're just reading out the X and Y coordinates and not the Z one. And we could also define the Z one as 1. Here, for example, we are just reading out the X, Y coordinates of the vector 3 and then writing the Z and W coordinates as 1. But we don't want that. We just want the full vector 3. We want our color to work. And for this, again, remember, color is defined by the fragment shader. Here you can see. So we need to pass the data from the vertex shader, which is not difficult at all. What we're going to do is we're going to write here out vec 3 v.vertex color. Here we're going to say that v vertex color is equal to a vertex color. So the v vertex color attribute of the specific vertex is equal to the color in the attribute. Now let's go to the fragment shader. Fragment shader will look very similar. We'll define the version. And now instead of the input with the fragment shader, here we're going to define the output. So the output layout 0 will be our F color, so the fragment color, which will be a vector 4, so RGB and alpha. Then we have our inputs from the vertex shader, which is the vec3 vertex color, and we're going to write another void main. And here we're just going to set F color equal to vec4 from the vertex color, and the alpha will be 1. This is our final fragment shader. And this is our final vertex shader. And now if we go back to our program, we can now use this shader. Let's go down here. Now here we just simply need to bind our shader like that. Now if we were to run this, you can see our square now has color. And very interesting, you can see that the color flows from one to the other. This is the interpolation OpenGL does automatically when it comes to drawing fragments. So if it needs to find out what values you use for a specific fragment, it will mix the values from all 3 vertices depending on how close they are. So if it's near to this red vertex, it's going to be really red. And if it's near to the green one, it's going to be really green. I hope all of this made sense. Setting this all up always takes a little while and it's a little complicated. If you have any problems, please tell me in the comment section, and thank you for watching.